one day someone asked, what good is general relativity? And after a few minutes of discussion, which I was listening to, they decided it's not much good except maybe for cosmology. So out of a perverse reaction to that, I ended up going to graduate school to study general relativity in Syracuse under Peter Bergman. Rich Isaacson told me he had a similar experience. He was a graduate student at Stanford, and his advisor was Leonard Schiff, and he asked Schiff, what about me going into general relativity? And Schiff said, if you're interested in physics, stay away from relativity. It's the province of mathematicians, and no physicist should enter. So Rich Isaacson had the same perverse reaction. He switched to Maryland and became a graduate student of Charlie Misner, which is thank goodness for LIGO, because without Rich Isaacson's defense of LIGO at the NSF, it never would have existed. So perhaps Schiff was right in 1962 when he told that to Isaacson, but today, of course, it's become a respectable part of physics and astronomy. Now, when I went to Syracuse in 1960, the main activity of Bergman, Komar, and Arnowit that were there was quantization of general relativity. And they had gone through about 10 different ways that they couldn't quantize general relativity, and it was hard for me to get interested in that. But that was a golden era for the field. And at that time, Ray Sachs, Roy Kerr, and Roger Penrose were all long-term visitors at Syracuse. And Ray had been part of the Bondii-Sachs description of gravitational waves. Roy had found the solution for the rotating black hole, and Penrose had done just about everything new, asymptotics and compactifying null infinity, the black hole singularity theorems, and spinors, which later turned out to be twistors. So my PhD thesis was the asymptotic behavior of coupled gravitational fields using the Bondii-Sachs formalism. So basically it was a multi-messenger version of the Bondii-Sachs work. And what we did was integrate electromagnetic fields and other matter fields into the characteristic initial value problem. So let me explain what the characteristic initial value problem is. Instead of using space-like hypersurfaces to evolve on, you use no hypersurfaces. Is this working? So you introduce a family of no hypersurfaces. Might be the initial no hypersurface labeled by U equal U0, and then these other no hypersurfaces act like retarded, the U on those surfaces act like a retarded time coordinate. And then you introduce an aerial radius along the no hypersurfaces that goes out in the no direction. It measures the area of the cross-sectional spheres. And the other angles are the two angular coordinates which label the no rays that are on the spherical cross sections. And the characteristic initial value problem consists of giving data on this initial no hypersurface and then propagating it up to the future no hypersurfaces. So that's the general idea. And in the Bondii-Sachs formalism, you do this in curved space. Again, you introduce a curved space family of no hypersurfaces with spherical cross sections. Use the aerial coordinate in curved space along the outgoing null rays. So that's measuring the surface area of the spheres. And then you again use the same angles corresponding to in standard coordinates to theta and phi to label the null rays. And that leads to a metric of the Bondii-Sachs metric of this form. Certain components vanish because of the null conditions. R is the null direction, and as a result, the RR and RA components of the metric vanish. And Bondy, the use of an aerial coordinate means that the determinant of the two-dimensional metric, which would be the entire two-dimensional metric is R squared HAB. So you make the determinant of that to be R squared. So the determinant of HAB now loses any dynamical freedom. It just becomes the determinant of the unit sphere metric. So that counting, you have 6 metric functions: V, beta, this vector field UA on the sphere, and HAB, which has 2 degrees of freedom since its determinant is trivial. And it's these 6 metric functions that you want to use for an evolution scheme. And it turns out to be probably by far the simplest evolution scheme you can have for Einstein's equations. So you write down Einstein's equations with here we are coupling them to a matter tensor. And you decompose these now into 2 types of equations: main equations, which are the R components of the Einstein equations, and also the trace-free part of the angular components. So then you look at the Bianchi identities, and if you look at the Bianchi identities that are satisfied, along with the conservation of matter, you find out that as a result of the Bianchi identities, one of the remaining Einstein equations is trivially satisfied. The trace of EAB of the angular components is 0. And the other equations are satisfied up to a radial derivative, so that if you just impose them on any value of R, any world tube at a given R, then they'll be satisfied everywhere. So by integration, what you do is you just impose these what are called conservation conditions on some world tube, and if the world tube is at now infinity, these give the conservation laws, flux conservation laws for energy and angular momentum, and that's what led Bondy to his famous mass loss equation in terms of the Bondy-News function. So these are the main equations that form the evolution system for the Bondii-Sachs metric. Now again, coming back to the metric, the main equations themselves separate into 2 types. First, the hypersurface equations, which are the R components, and then the evolution equations, which are the angular, trace-free part of the angular components. And the characteristic initial value problem works this way. Given free data for HAB, that's 2 pieces of data since the determinant is trivial. Given this data on a null hypersurface, the hypersurface equations are just a sequence of radial ODEs for the remaining 4 metric variables. And by a sequence, what we mean is that once you give HAB, then the first hypersurface equation is just a radial equation for beta. This operator H beta is just a hypersurface operator. So given HAC on the null hypersurface, you can determine this piece of the right-hand side. And if the matter fields are fields that travel along the null cones, like Klein-Gordon fields or electromagnetic fields, the same holds true for the matter terms on the right-hand side. So So the first hypersurface equation tells you what beta is, and then once you know beta and the initial data, HAC, the free data, then you have another equation that's just an ODE for the vector UB. And then once you solve that ODE for the vector UB, you get another ODE for the remaining hypersurface quantity V. And again, this all holds for all the right-hand sides if the matter fields have characteristics along the light cones. So if you're given coupled fields of that type, if you're given electromagnetic fields or Klein-Gordon fields of that type, then given the initial data on a null hypersurface and the boundary data on some world tube gamma that you need to supply the integration constants for these ODEs, then you determine then the evolution equation determines the time derivative of the initial data. So let me go to the evolution, how the evolution equation works. Again, to simplify, what you do is the usual trick of taking the HAB, which is basically the gravitational strain tensor, and construct a polarization diode, a null polarization diode, to make it into a to make it into a the evolution equation into a complex equation. So basically, that knocks out the trace term in the evolution equation. It just becomes this complex equation. And when you write that down, that evolution equation itself is now a radial ODE for the null data, HAB, in terms of things you've already determined on the right-hand side. So given the boundary data for the integration of this equation, that leads to a simple update scheme for the free gravitational data HAB. So basically, you've got a constraint-free characteristic initial value problem. You give HAB on some initial surface along with the matter variables, and then you can just chug along in time. Now, the first application of this was to the Bondii-Sachs theory. Back in those days, quite some time ago, I think it was around 1970, Bondii-Sachs noted that in their scalar tensor theory of gravity, if you had collapse of a neutron star, the radial modes, the spherically symmetric radial modes of the neutron star would give rise to a scalar component of radiation. And in the theory, that would damp in less than a second, and it would give an intense short burst of scalar type gravitational radiation. And Dickey thought that would be possibly detected by an antenna type, a Weber type antenna. Now, originally Dickey thought that the response to the spherically symmetric oscillation mode would be spherically symmetric, but using a Bondii-Sachs analysis of how the irradiative component of the Riemann tensor behaved, we were able to show that the radiation really wasn't spherically symmetric, but was transverse to the propagation direction and axially symmetric about that direction. And Dickey was very gracious in acknowledging us for that. Okay, I didn't say anything about numerical work yet. This is, I couldn't resist showing this slide. It was one that my wife had made up for me, and I was going to use for a talk at the 1970 Spanish Relativity Conference in Granada. And it was on the topic of mathematical versus numerical relativity. And my wife took wormholes seriously. She put a worm in them. Unfortunately, we weren't able to make the trip to Spain because she became ill, but I gave them that slide, sent them that slide, and they used it for the front cover of their proceedings. I told her, I think this was supposed to be an Einstein version of Newton under the apple tree. Yeah. So the major, coming back to the numerical side, the major contribution of this Bondii-Sachs formalism has been to what's called Cauchy characteristic radiation extraction. And this is a world tube null cone problem. So you have an inner world tube with the null hypersurfaces extending out of it to infinity. And inside the world tube, you carry out a Cauchy evolution by any Cauchy code that you happen to have. And that gives you the boundary data on the world tube. Gives you all the boundary data on the world tube that you need to carry out the characteristic evolution. So this boundary data supplied by the Cauchy evolution gives you all the integration constants you need for the hypersurface and evolution equations. And the evolution equation then tells you the time derivative of HAB, so that you get a finite difference approximation for the value of HAB on a next hypersurface stepped up in retarded time. So given the initial and boundary data given the initial data and the boundary data supplied by the Cauchy evolution, you can iterate this in sequential order to form a finite difference evolution scheme for the exterior using the Bondii-Sachs formalism. And this was implemented as a stable convergent code, where you propagate the solution exterior to the world tube out to Scri plus, where you compute the radiation strain. And that was first done at Pittsburgh by a finite difference scheme, and now it's been also done in a much more advanced way using a quasi-spectral scheme in terms of the spec code that's been primarily centered at Caltech. So the advantages of Cauchy characteristic extraction are that, first of all, you can, since the solution is propagated all the way out to future no infinity, you can use Penrose compactification to map Scri plus into a finite grid boundary. And once you have that, you can work out what the Bondii-Sachs asymptotic symmetries are at Scri plus. And the Bondii-Sachs symmetries correspond to that group corresponds to a Poincare group plus a supertranslation subgroup. And the Poincare subgroup allows you to identify inertial coordinates corresponding to a distant inertial observer. So you can transform to the proper coordinates to describe the strain in the right coordinates that a detector would be using. And you can also So basically what you can do is you end up with the Bondy-News function in the radiation strain accurately up to any numerical error. There's no error of an analytic sort in the scheme, which involves the choice of what the right inertial coordinate system is, or the right gauge. Now the Poincare subgroup of the Bondii-Sachs group allows you to provide a geometric definition of energy and angular momentum in a similar way that you use that group to define angular momentum and energy momentum in special relativity. But the Bondii-Sachs group contains that supertranslation group too. Now the supertranslation group is what takes the retarded time at infinity and shifts it up and down in an angular dependent way. So it's a time-dependent shift of the spherical cross sections at null infinity. And what that does is it introduces ambiguity in the origin that you want to associate with the definition of angular momentum. And this is a rather important aspect of the Bondii-Sachs group. And this supertranslation shift is also related to the gravitational memory effect. Now what the shift corresponds to is, if you look at the radiation strain at infinite future retarded time and infinite past retarded time, the shift in that shift is what corresponds to the radiation memory. And physically, what it would do if you had a mass and two masses in the radiation zone, it would, after the radiation passes, it would take two masses that are initially like this and give some relative separation to the final position of the two masses. Now, what causes that in astrophysics, the main astrophysical process that can lead to this gravitational memory is a burst of matter coming out of a system. So the ejection of matter is what gives rise to this memory effect in an astrophysical context. Now, if this occurs and you have this memory effect, then even though you might be confident about your definition of angular momentum at the early time, or u equals, say, early retarded time at minus infinity, and even though you have a flux conservation law for angular momentum, so you can now do the bookkeeping on how the angular momentum changes from the early time to the late time, the problem now is that the early time and late times don't have the same Poincare group, don't have the same BMS group. They differ by a supertranslation. So even though you have a conservation law for angular momentum, the angular momentum that you're conserving is not the one that the late time person is going to pick out, because it'll be a preferred Poincare group at the late time that differs from the preferred Poincare group at the early time. So that doesn't give any ambiguity in the definitions of energy or momentum, but it gives ambiguity in the definition of angular momentum. And it's kind of like the ambiguity that when you define angular momentum, you need a point to define the angular momentum about, and you can translate that point. But now this is more complicated because you have this super translation rather than a regular translation. So that's one of the effects, asymptotic effects, that is interesting and hasn't really been very well, it's only been roughly explored in the numerical simulations. It's something that should be looked at more carefully in the future. Now I want to get back, since I said this my thesis was on a multi-messenger version of this, what the electromagnetic analog of the Bondii-Sachs formalism is. Now, you can do this in full general relativity, coupling the Einstein-Maxwell fields, but to keep it simple, let me just explain how this works in the Minkowski case. So again, we have the null cone with the null coordinates on it, and we will assume that the that all the sources of the electromagnetic field are inside a world tube of some radius r, just to make matters simple. Otherwise, we'd have to worry about the charge and current sources along with the electromagnetic field. Or if there weren't any charge and current sources, we could just consider this system all the way down to collapse the world tube down to some vertex of the null cones. But in a practical situation, there will be, where you look at electromagnetic theory, there will be sources. So in this Bondii-Sachs version of Maxwell theory, you represent the Maxwell tensor in terms of a vector potential, and that leaves you with this gauge freedom of adding on a gradient of a function gamma, function lambda. And what the analog of the Bondii-Sachs coordinate conditions are using the R dependence of this gauge function to integrate, take the R component of the vector potential, depending upon what gauge you're on, integrate it, choose that lambda, and then as a result of that gauge transformation, you end up in a gauge in which A sub r is 0. So it's similar to the analog of the Bondii-Sachs coordinate condition that R is the null direction, so you can think of this as a null gauge. Now, that leaves you with some remaining gauge freedom. So now the gauge function can be a function of u. This should be the angles theta A. And you can use the u dependence here now to set the u component of A equal to 0 on any world tube. It's the simplest one to pick is at the world tube on Scry at future no infinity. And then what you're left with at the end, after you've done that, is a gauge function that's just a function of the angles. And this turns out to be the Maxwell analog of the supertranslation freedom in the Bondii-Sachs gravitational case. Now, to look at how the Maxwell equations work in this Bondii-Sachs analog, and here I'm looking at the current free case. You use the fact that the divergence of these equations is 0. That's the analog of the Bianchi. That's the analog of the Bianchi identities in Maxwell theory. And when you write that divergence out, you get these three terms. So the strategy now is to designate this term and this term, the EU and the EA, as the main equations. And then as a result of that, you get this equation, the ER component will be satisfied if it's satisfied on any world tube. So its R derivative will be satisfied, and so that equation now becomes a conservation condition, which you have to only imply on a single world tube. If you had taken that world tube to be the vertex, if you extended your null cones all the way down to the vertex, then that equation just becomes a regularity condition at the vertex, in the neighborhood of the vertex. If at infinity, that equation reduces to charge conservation. So the main equations, now the U and the A component of these equations, again form a hierarchy, just as in the gravitational case. The U component is a hypersurface equation, and what it does is that if you take the initial data, which consists of the angular components of the vector potential, then you just get an ODE for A sub U. So this is, again, not the right-hand sides now are simple to write out. This is a hypersurface operator, just involving angular derivatives and radial derivatives on the null hypersurface. So given the free data AB, you find out that you find out what the U component is, the remaining component, in terms of an ODE. And the evolution equation now gives you a radial ODE for the time derivative of the initial data. And these terms are the right-hand side. Again, they're all hypersurface terms. This operator is just the covariant derivative on the unit sphere. And so given now AU and the initial values of AB, you can integrate this equation given boundary conditions to find out the time derivative of AB. So again, that leads to a constraint-free version of the characteristic initial value problem, just as in the gravitational case. So this is probably the simplest version of Maxwell's equations that you could write down. So so this can be applied now to a electromagnetic version of Cauchy characteristic extraction, where you extract the electromagnetic radiation at infinity. And what you need now is all you need is the initial no data, the unconstrained no data consisting of the angular components of the vector potential, and the initial boundary data, which the derivative of the U component, which represents what the interior sources are, and this world tube data that tells you what the dynamical degrees of freedom are doing on the boundary, plus some gauge information. You can pick, this is free gauge information that you can, again, the U component can be taken, on any given world tube can be taken freely by gauge transformation. So in the Cauchy characteristic extraction scheme, all these world tube data would be given by the interior Cauchy evolution of the system of the interior where the charges are. And now to update the system, you just go through this sequential integration scheme. Given the initial data, you can integrate this in terms of the boundary conditions to find the remaining U component on the initial hypersurface. And then the evolution equation gives you a radial ODE for the time derivative of the initial data, where you've determined the right-hand side. So now you know that in terms of the boundary data, you know the time derivative of AB. So that gives you a finite difference approximation for updating AB to the next retarded time step. And I won't go through this. The conservation conditions are, if you didn't know the interior solution, if the Cauchy solution wasn't supplying the interior solution, you could use the conservation condition to update this quantity. So what you end up is with a finite difference approximation that allows you to iterate in time to find the no data AB at any future time in terms of the, and the remaining component at any future time in terms of the initial data. So this is all how it works in principle, but there's a lot of unfinished business here because no one's ever coded this. It would be a nice thing to code it just in the Minkowski space. It would be a nice problem. in the coupled Einstein-Maxwell case, everything in principle goes through just the same. It's just that the algebra becomes immensely more complicated. And in the Einstein-Maxwell case, a code like that would allow you to investigate what the nonlinear interactions were between the gravitational modes and the electromagnetic modes. And let me talk about one other thing in the electromagnetic case. And this is the analog of radiation memory that I mentioned in the gravitational case. This analog was first pointed out by Lydia Bieri and David Garfinkel. And in terms of the vector potential, the radiation field at null infinity is given by just the retarded time derivative of the vector potential. Normally, this would be an antisymmetric derivative, but the U component can be set to 0. So this angular component of the electric field is just the transverse radiation field at scry. And if we integrate that using the force law, that Q times that would give the acceleration of a nearby charge, then we'd find out that if when we integrate that, the vector potential changes between infinite past and infinite retarded time, and we carry out this integral of the electric field, we just get the change in the vector potential between the infinite future and past. And if that's non-zero, we get a change in the velocity of a charge that would be in the radiation zone. So this is much more dramatic effect in the memory effect in the electromagnetic case than it is in the gravitational case. In the gravitational case, memory just gave rise to a net displacement of a particle in the radiation, of particles in the radiation zone. Here you actually get a kick. So if after the radiation passes, if you had a particle that was initially at rest, then the particle would end up moving. Now, one of the interesting things about this is that there's a patent to this memory. The radiation can be decomposed into the usual E and B modes by decomposing the angular component of the vector potential into a gradient, or what basically in 2 dimensions is the dual of a gradient, or a 2-dimensional version of a curl. And the gauge freedom at scry now, adding on a gauge function that's just a function of angle. That's this analog of the supertranslations in general relativity. Gives rise to a E-mode type change in the vector potential, but it's a time-dependent E-mode change. And as I said, that's the analog of the supertranslation shift. And the way you get this now, the way this would be produced, this electromagnetic memory, is similar to the gravitational case, where you have to, instead of ejecting masses to infinity, you eject charges to infinity. So if some astrophysical system actually ejected a charge to infinity, then the radio wave coming from that signal, or the electromagnetic, whatever frequency the electromagnetic wave would have, would show this memory effect. And if you look at the effect in the case of a dipole radiation, so here's how the electric field is given in terms of the second derivative of a dipole moment, and it's proportional to the charge that's ejected this would be the ejection charge times the velocity of the angular velocity of the charge, then if we integrate that, then the memory effect would just be due to the change in the velocity and the angular velocity of that charge. So if you look at that for a charge ejected in the z direction, then the memory effect is given by this formula. But the fact that it's a gradient, you can see it's a pure E-mode type pattern. It has a pure E-mode type pattern on the sky, and it's proportional to the charge that's ejected and the velocity at which it escapes from the system. So it's one of the interesting things that haven't been explored is whether this really can be detected. Can you see that in a radio waveform? It must be there. I mean, in principle, it has to be there, but I don't think anyone has ever looked for it. And then there are other questions. Is the kick due to the electromagnetic memory strong enough to affect the dynamics of any plasma nearby the system that ejected the charges? And are these escaping charges from a burst the only source of electromagnetic memory? And are there any physical, realistic sources of B-mode radiation memory, or does it have to be E-mode? And probably a lot of these things are hard to do. I imagine that some of these effects may be negligible in practice in an astrophysical context, but it'd be interesting at least to know the numbers. So those are some of the outstanding questions, and I'll go on to one other issue, and this is the deficiency of the Bondii-Sachs formalism. The Bondii-Sachs formula uses this aerial coordinate, which I called R, in order to label the distance along the outgoing null rays. Now the problem is that if you, in the black hole context, whenever you have an apparent horizon, R becomes a singular coordinate. The affine parameter lambda always is a good coordinate along any null ray, unless you reach something like a singularity. But on an apparent horizon, dr d lambda equals 0, so the Jacobian between using lambda and r breaks down. And since lambda is always a good coordinate, that means the aerial coordinate breaks down when you reach a horizon. So an alternative is to use a characteristic initial value problem based upon the affine parameter, what I call the affine-null version, instead of the Bondii-Sachs version based upon R. And both have the same, both would have the same advantages at infinity. You can compactify it, get the Bondi-Metzner-Sachs group, look at the inertial frames, define energy momentum, angular momentum, and all the other things like the Newman-Penrose constants. But the Bondii-Sachs system has that one very special advantage that all the main equations form a hierarchy. So you can integrate them one at a time, get the first variable, put it into the next equation, get the next variable, and so on, as I've shown. It turns out that you can't do that in the affine-null system. That the equations don't form a sequential set in the same way that you get a hierarchy of ODEs in the gravitation in the Bondii-Sachs form. And so if your only two alternatives, either you have to try to take that set in a non-sequential form and try to make a code out of it, which might or might not work. We always thought that the reason that the Bondii-Sachs code was so robust was the fact that you had this sequence of radio ODEs. Now, you can define some new variables in the affine-null system so that you restore the ODEs, but they're non-obvious choice of variables, and this has never been coded except for the case of spherical symmetry. So another outstanding problem is, can you really get a numerical implementation of this affine-null system outside of spherical symmetry? And there are a lot of other outstanding problems, but I better stop here.